Today we are going to talk about whether or not two events are said to be independent. So when two events, for example, E and F, are said to be independent, it means that the outcome of one event does not influence the outcome of another event. So there's two ways that we can actually prove independence, and we'll talk about both of them in the notes today. The first way is dealing with conditional probability. You'll see here the probability of E given F equals E. Basically, what this is saying is that it does not occur that event F has happened. It doesn't matter that event F has already happened. The probability of E remains the same. And this works vice versa as well. So the probability of E given F equals probability of E. Same thing, probability of F given E equals probability of F. There's one other way to prove independence, and that's using the multiplication rule. So this is your first method. And then here's your second method. We'll call it method 2. So the multiplication rule means that you can multiply the probabilities of two individual events happening, such as the probability of E times the probability of F, and get the intersection of those two events. So the probability of E and F when you're looking at a two-way table. And again, we'll go through both of these methods using some actual examples. Let's just kind of talk about what it means to be dependent or independent, though. So some examples of events are which likely to be dependent. The event that a student spends more time on homework and studying, and the event that the student's test average goes up. The event that the amount of snow is above average in a given winter, and the event that the number of snow shovel sales is also above average. So obviously the more snow we get, the more snow shovels people are out buying, or the more snow blowers. Now for independent events, so one example is the event that a 2 is rolled on the first roll of a dice, or that should say die, and the event that a 2 is rolled on a second roll of a die. So if you're rolling a die multiple times in a row, the outcome of one roll should not impact the outcome of next. You still have 1 in 6 opportunities, or 1 in 6 values that you could get. The other example is the event that I don't know what's going on with these notes. I apologize. Jose Bautista hits a home run and Tiger Woods scores a hole-in-one in the same week. So home run, obviously referring to baseball. Tiger Woods, hole-in-one, we're talking about golf here. These are two completely different individuals. So these events would be independent. There's a few more examples down here. So I'll go through the first few, and then I want you to try the last few. So rolling a 2 on a die and selecting a single card, let's say a heart, from a deck of cards. Well, again, if you roll a die, that should not impact the probability of getting a heart when you're selecting cards. So these would be independent events. Having a Jewish surname and attending Hanukkah celebration. Well, if you have a Jewish surname, there is a higher chance, not necessarily given, but there's a higher chance that you also celebrated a Hanukkah celebration. So these would be dependent events. The gender of my firstborn child, the gender of my brother's firstborn child. So genders are actually completely independent no matter what, even if you're referring to the same person. So these would be independent events. And then we'll do maybe one more. Let's skip to, how about 5? So born and raised in Florida, attending the University of Miami. Now, if you are born and raised in Florida, and the University of Miami is also in Florida, there is a higher probability that you might attend the University of Miami that you live in Florida, such as compared to someone in Illinois. So these are dependent events. Now, how do we prove whether or not events are independent or dependent? So there's 2 different ways that you can do so. So here we're going to be looking at obedience schools for dogs. I've already filled in most of the notes, so you can pause it as you go along to kind of copy this in, but I didn't want the video to be too long here. So it says Obedience School for Dogs. It's a small franchise that offers obedience classes for dogs. Some people think that larger dogs are easier to train and therefore should not be charged as much for the classes. To investigate this claim, dogs enrolled in the classes were classified as large, 30 pounds or more, or small, under 30 pounds. The dogs were also classified by whether or not they passed the obedience class offered by the franchise. So all of our information is giving in percents, so I just did it out of a hypothetical 100. It says 45% of the dogs involved in the class were large, so total large is 45. 60% of the dogs passed the class, so for pass the class, total is 60. And then records indicate that 40% of the dogs in the classes were small and passed the course. So 40% passed and small, that means 28% or 20 dogs were large and passed. And it looks like I'm still missing one value here. So if I do 40 plus 15, we get 55. So 55 were small dogs. So here's our first method of proving independence. So we're trying to determine, do you think dog size and whether or not a dog passes the course are related? The first thing I did was just calculate the probability of passing the course. So 60 out of 100 dogs pass, so that's a probability of 0.6. Then I said, okay, well, what is the probability of passing given I've selected a large dog? So now I'm only looking at those large dogs. So remember, we're narrowing it down to just this row here. So out of those 45 dogs, 20 passed for a probability of 0.44. So because 0.6 does not equal 0.44, I would say therefore the events are dependent events. Because what this means is the fact that it was a large dog means the probability of passing actually went down. So in comparison to everyone altogether is 0.6, but for just those large dogs, the probability of passing was 0.44. So the probability is lower given we selected a large dog. So do you think large dogs should get a discount? Well, if the probability went down, I would probably say no, because that was under the assumption that large dogs were actually easier to train and therefore more likely to pass. Now, the second method of proving independence has to deal with our intersections and multiplication. So here the question, do you smoke, was asked of 100 people. Results are shown in the table below. So we have yes, no, and then male, female. So determine whether the event selected individual as a smoker and selected individual as male are independent or dependent events. So what I did here is I multiplied the probability of the individual events together. So the probability of smoker times the probability of selecting a male. So 31 over 100 times 60 over 100. And I wanted to see, did that equal the intersection of the probability of smoker, so yes, and male, so 23 over 100. Now, when you multiply these and make sure to use your parentheses here, you get 0.186. Again, because that does not equal 0.23, that means that these are dependent events. So the last example here, I'm going to actually show you both methods. So it says use the data given in the table for the sample is student owning a smartphone independent of grade level. So we have own a smartphone, do not own a smartphone. And then 10th, 11th, and 12th graders. And then the totals have been filled out here. So method one is over here on the left. So first thing I did was just calculate what is the probability of owning a smartphone. So I got 594 over 1,089, so 0.545. Then I looked at a conditional probability. So the probability of owning given I've selected an 11th grader. And it shouldn't matter in this case if you chose 10th, 11th, or 12th. It's going to lead you to the same outcome. So if I narrow it down to just those 11th graders, so out of the total of 352, 192 of them have a smartphone. That's a probability of 0.545. Because these two probabilities are equal, then we can say that they are independent events. Now, method 2, dealing with our multiplication, would go like this. So if I took the probability of owning, for this example I chose a different grade just to kind of show you here, times the probability of being a 10th grader, does that equal the intersection of owning and 10th grader? So the probability of owning a smartphone was 594 over the 10,000 or 1,089. The probability of choosing a 10th grader was 374 over 1,089. And then that intersection, the probability of owning a smartphone and being in 10th grade, was 204 divided by 1089. So once I calculated those, again, don't forget those parentheses, I found that those were equal probabilities. That means that the two events are independent events. Now that I've showed you the two methods, what I'd like you to do is go through the worksheet assigned for today and try using both methods. So I think there's just two examples. Try doing one of each, because then in Delta Math, you will have some examples of each as well. Have a good rest of your day.